Hey everyone, Mr. Fransky here. Today we're talking about testing binomial and Poisson distributions, and we're going to start off with looking at a deck of cards. So we have what we're calling a fair regular deck of cards here, and so that must mean that there are 26 black and 26 red cards. And Mr. Fransky thinks his deck is fair. So there's an even chance of picking a red or a black card, but Mr. Radcliffe thinks the probability of picking a black card is higher than the probability of picking a red card. And we're going to test this at the 5% level of significance. So often IB questions like this will not specifically mention it's a binomial distribution. But what we're looking at here is we're going to pick some cards. We're going to end up drawing 8 cards. And we're going to look at the proportion that we have. So it's a fixed number of trials. We expect the proportion to be 50%. And so we're going to be able to test this with a binomial distribution test. So the null hypothesis here, of course, is that P is equal to 0.5 for picking a black card. And in other words, the deck is fair. And then the alternative hypothesis, so what Mr. Radcliffe is saying, Mr. Radcliffe says that he thinks the probability of picking a black card is higher than 0.5, greater than 0.5 for the black card. And let's say that we draw 8 cards. Okay, so we draw 8 cards, 1, 2, 3, 4, 5, 6, 7, 8, and we're going to look at the number that are black, right? And the question is, how many of them need to be black in order for us to doubt the null hypothesis, right? And the weird thing here is that if we think like what we've done with normal distributions, so for normal distributions or t distributions or chi-square, there's always kind of like a cutoff value that has exactly 5% in the tail, right? So like if this was our example, we're doing something 8 times, maybe like if you get 6.27 black cards or something, that'll have exactly 5% in the tail. But the problem is it's discrete, right? This is not a continuous distribution. So we're going to get a specific number of black cards. So we can only get 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 black cards, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8. And it's possible that if we cut off like after 4, that the probability on the left side may be, I'm going to make these numbers up, but let's say it's like 0.6 or something. And on the right side, it's 0.4. And if you cut off after 5 cards, maybe the probability to the right is like 0.27 or something, right? And you can see what I'm getting at is that wherever you cut it off, there's basically no chance that you're going to get exactly 5% to the right, right? It's going to be, at some point, we're all of a sudden going to be less than 5%. And that's exactly what we're looking for. We're looking for some value that if we get more than that number or equal to that number, we're at less than 5%. So I'm going to erase that, and we're going to try to figure out what that value is. So if we think about this, right, so I'm going to draw my timeline again here. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So if we can figure out what that value is, where we're at less than 5% on the right, that means on the left side, we must have more than 95%. So one way to think about this is we're going to do a binomial CDF where we're picking 8 cards. Our probability of success is 0.5. And then we're going to look at what happens if I do different x values. So I might want to see what happens if I pick 0 or 1 or 2 or 3, right? And that's going to add up from 0 to 1 or 0 to 2 or 0 to 3. And I'm going to look for a value that's over 95%. So if I go to my calculator and I go to, easy way to do this is in a y equals. So I'm going to do just distribution, binomial CDF. Here we are. And I'm going to put in my n is 8. Comma, my probability is 0.5. If you have the list in your calculator, this will look a little bit different, but it's the same type of idea. And I'm going to do x, because I want to see what's the probability of getting up to 1 or up to 2 or up to 3 or up to 4. And then I'm going to go to my table. I'm going to check out my table set just to make sure it's good. Starting at 1 is fine, and changing by 1 is good as well. So I'm going to go to second graph to get my table. And you can see that negative numbers don't make any sense, right? Up here in the negatives, it's all 0, but the probability of getting 0 is 0.00391, and then 1, and then 2, and these are cumulative distributions. So by the time I get to 8, it makes sense that I have a total probability of 1, because I'm going to get 0 or 1 or 2 or 3, right? These are CDF values, so they're accumulating as we go. And what were we looking for again? We were looking for the first value that's over 95%, because that means on the other side will be less than 5%, right? So we're looking for that cutoff value. And it looks like 6 is the first time that's true, right? So if this is like the 6 value, let's do that in a different color. So if this is the 6 value right here, then if I get 7 or 8 cards, I would be at a probability of less than 5%. And I could have done this that way as well, right? I could, if I go into my y, let's do y2. I could do 1 minus binomial CDF, so distribution, 1 minus binomial CDF of 8 draws, and our probability of success is 0.5, and x. And I want to illustrate a really important point here with when you do this. So when I go into my table here, I'm looking for now a value in my y2s that is under 5%. And we see the first time we see that is when we get to 6, but I want to write down exactly what that was, right? So what we just found out was that 1 minus binomial CDF at x equals 6 gave me a number that was less than 5%. That was 0.03516. So what that means is that this is 7 or more, right? This is 7 or more because of the way that binomial CDF works, right? They're adding up to 6. They're saying that if I take that away, there is a 0.03516 chance that I'm in that top tail. So it's not 5%, but it's the first number that's less than 5%. So if we answer our question here, the answer to this question is that the critical region is if x equals 7 or x equals 8. That's my critical region, right? That's my final answer for what the critical region is. So in my draw of 8 cards, if I get 7 or 8 black cards, that would be enough to say that Mr. Radcliffe is correct, that we have too many to say that it's a fair deck, okay? So 2 ways to do it in the calculator, and it's kind of tough to see that. I'm actually gonna take a screenshot here so we can save that. But it's, you just have to think a little bit about how kind of that binomial PDF and CDF works. And if you're doing a 1 minus, you just have to be a little bit careful about how you keep track of that data, right? So I'll put a little guy in here, see if we can sneak it in there. All right. So now, what is the actual level of significance for the test? Well, we just found that out, right? We want alpha to equal 5%. But actually, if I get a number that's 7 or 8, we know that the actual alpha value is going to be 0.03516. And the easiest way to do this is when you're in your calculator table. When you're in your calculator table here, you're just finding the first value that's less than your alpha, right? Less than our 5% value for alpha. And that's going to be the actual significance level for the test. So we're actually even stronger than a 5% test, right? And as we know, in a normal test, the type 1 error is just alpha, right? Alpha equals the type 1 error. But in this case, this is the probability of a type 1 error. The type 1 error is going to be 0.03516. So it's reduced our probability of a type 1 error because it's impossible to get exactly 5% because that would have to like cut the 6 in half or something, right? And that's not possible. Only in the 7 or 8 is when we're going to reject the null hypothesis, and that'll happen with a true probability of 5%, only 3.5% of the time, right? Cool. So say you draw 8 cards and all 8 of them are black. Okay, interesting. So the probability that happens, so that would be that we get 8 or more, which is kind of boring for this one because 8 is the biggest. 4, 5, 6, 7, 8. So the probability that we get 8 or more, so the way I would do that is 1 minus binomial CDF when x equals 8. And we can actually see on our calculator over here that value is going to be the probability, 1 minus the probability of binomial CDF at 7, apologies, because we want 8 or more. And there's only one value for that, right? The only value for that is 0.00391, right? So it's about 0.391%. And what that means is if this is a fair deck, if it's truly a 50-50 chance, if our null hypothesis was true, then the odds of getting 8 black cards is under 1%, which is really tiny, right? So our p-value is 0.00391 or 0.391%. So the conclusion then, so since p is 0.00391 is less than our alpha value, which is 5%, 0.05, we reject the null hypothesis and claim sufficient evidence that P is greater than 0.5 for picking a black card. So the deck isn't fair. And that kind of makes sense, right? If you're going to pick 8 cards and they're all black, like, I would not believe that's a fair deck, right? That's going to happen very, very rarely. In fact, exactly 0.391% of the time. And we also could have done this with the critical region, right? Because X equals 8 black cards. And, whoops. And the critical region is X equals 7 or X equals 8. Same deal, we reject the null hypothesis. And hopefully that's helpful for how we do a binomial test. The trickiest thing is the different way to use our calculator to be able to find that new alpha value and our critical region.